Hi, I'm Shreyas. I'm a graduate student at San Jose State University, and this is the demo of my final project for EE278. This project is intended to highlight the difference in the speed of operation between the hardware and the software counterparts. I'll be using a Nios 2 processor to download the software, and I'll be working on DE2-115 board, which uses Cyclone 4. Let me open my software project. The first step is to create the system using Qsys. This is the system that I've already built, so I will just import the system and explain the components as we go. The clock module is external to the FPGA, and this is connected to all the components in our system. This is the Nios 2 processor, the on-chip memory, the JTAG UART, and the performance counter. Clock and the reset signals, which are external to the FPGA, are connected to all the modules. The Nios 2 processor controls the data and the instructions. Both data and instructions are connected to the on-chip memory, where the code basically resides. The data is in turn connected to all the modules. Once all these connections are made, we have to connect the interrupt signal from JTAG UART to the Nios 2 processor, and we have to assign the base address. The system automatically generates these base addresses automatically. The next step is to generate the system. You go to the generation tab and click on generate. It asks if you have to save, yes, and generate the system. This takes a while. There are no errors in the generation, so you close this window, go back to your Qsys 2 files, and we'll have to add the QIP file that has been generated. I have already added this to the project, so this is what we get. And the next step is to create top module. The only external signals here are clock and reset, so we connect clock to the external clock signal and reset to VCC, because we are using a reset on the negative edge of the clock. Set this block as the top module for the project and compile the project. The compilation takes a lot of time. Once done, we'll have to download the program to the on-chip memory. Compilation was successful, so open the programmer, and this is the SO file generated. Make sure that the USB blaster is installed and download the program. The program has been downloaded successfully, and now open Nios 2 Eclipse, and this is implementation of the FIR filter has been done using the C language, and performance counters have been included to measure the performance. The SOPC info file that will be generated after the compilation of the code, all the components will be used to create the project in Nios 2, and this is the file that I've used. Once the project NC is created, we build the project. Build is successful, and we run the project as Nios 2 hardware. This is the run configurations window. As you can see, there are no target connections. Just refresh the connections. We can see the USB blaster. Make sure you have checked ignore mismatched system IDs and mismatched system timestamps. Apply and run. This is the output of the filter. The FIR filter output is -34, and the number of clock cycles this has taken is 228,981. This is a lot of cycles to compute the result. Let us now go ahead and check the performance by including a hardware accelerator to the system. The only difference here is the addition of FIR_128, which is the hardware accelerator. This is a custom component and is built using the Verilog files used to create a 128 tap FIR filter using a single MAC. The top module will be the interface file. These are the ports for the FIR interface, and this is the final interface that is built. Once all this is done, we'll have to generate the system. After the system generation is successful, we have to follow the steps as before. We'll have to import the QIP project into the Qsys 2 system and create a top module, connect the clock signal and the reset signals, and make the pin assignments. Here the clock is the only external signal, so this has to be connected to pin Y2 in DE2-115 board, and compile the project. Once the compilation is done, the steps are as before. Open the programmer and download the code onto the chip memory of the FPGA. The FPGA has been programmed successfully, so we now go to Nios 2 Eclipse. We will have to create a new project using the SOPC file that includes the hardware accelerator, and this is the C code used to communicate between the FPGA and the Nios 2 processor. As you can see, these are the inputs that I'm sending to the FIR filter using a for loop, and after sending all the 128 inputs, I'm reading from the port to get the output of the filter. And this is as before. I'm using the performance counter to measure the performance. The base addresses for the performance counter and the FIR filter are set using the values from the Qsys. And to view the report in a formatted tabular column, I have used the perf print formatted report, which is an inbuilt function to customize or format the generated report. Now let us build the project, and once the project is built successfully, we run the project as Nios 2 hardware. This is the output of the FIR filter, which is -34, which is it's the same as before, but the number of clock cycles it has taken to generate this output is about 10 times less than that of the software counterpart. It is 22,850, whereas the software implementation without the hardware accelerator took about 222,000 clock cycles. So this is significantly faster. This hardware accelerator uses a single MAC, and the speed can be further enhanced by increasing the number of MAC units used to implement the hardware accelerator. Thank you.